Good evening, everyone. A warm welcome to INNOVATE X, proudly organized by the Microsoft Student Club of Wellassa University. I'm Lihini, and I'm excited to be your host for this fantastic session titled How LLMs Learn to Reason. We are going to look at how large language models are trying to think, respond, and even solve problems like human. Now, let's welcome the person who here to guide us through this journey. Please join me in welcoming Mr. Nirodya Pussadeniya. He is a co-founder and director of Synacal, where he leads a team building smart solution using AI and machine learning. He is a graduated computer engineer student at the University of Sri Javadanapuram. His research is all about helping machines understand language better, just like humans do. He has worked on many real-world projects using AI to support education and health and more. Mr. Nirodha is truly passionate about using AI to make a positive impact, and today we are lucky to learn from his experience. Let's warmly welcome Mr. Nirodha Pussadeniya as he begins today's session. Sir, the stage is yours.
Thank you very much for the introduction. First, I'll share my screen. Okay, so yeah, let me start the today's session. So when talking about large language models like GPT-4 and Llama or whatever, they have astonished us with their ability to hold conversations, answer questions, and solve problems in ways that seem very intelligent. And also, they often appear to think or reason through complex tasks. But what is actually happening under the hood when an LLM comes up with an answer? So, in this talk, we'll explore how LLMs work and how they reason from the core components of the architecture to the strategies that make them appear so clever. Right? So, we'll cover the basics of tokenizations, embeddings, and attention mechanism, and the transform architecture, and then discuss how those LLMs can be prompted to reason using methods like chain of thought and few shot learning. And then we'll dive into a recent study from Apple called The Illusion of Thinking, which critiques those actual reasoning capabilities of LLMs and shows where they fall short. And I hope by end of this talk, uh, you will get a kind of a basic understanding of how those LLMs think, where they struggle, and how we are trying to make them reason better. So before that, let me introduce myself. I'm Nirodya Pussadeniya, and I'm the co-founder of Synacal. Uh, at Synacal, we create practical AI and data-driven solutions for businesses especially in US and Hong Kong, and several fast-growing startups in Silicon Valley. So our work ranges from automated market research platforms to intelligent process automation tools, and all aimed at helping teams move faster and to cut manual effort and make smarter decisions. So I'll share what we have learned building these systems and to talk about where language-based AI is headed next. So thanks for joining me, and let's get started. So let's start with why large language models matter in the first place, right? So first, we all know that they can generate, understand, and even reason with human language or the natural language, something like English, it can be Sinhala or whatever the language. So that means the same model can draft an email or debug a kind of a Python code or summarize a research paper without retraining. The second thing would be they already show up everywhere nowadays, right? So inside chatbots, search engines, tutoring apps, coding assistants, or maybe they can be in research workflows. If you have used DeepSeek Chat or Microsoft Copilot or Google's Gemini, you have used an LLM that is in production. So third point would be they act as a kind of a bridge between all the text we humans have written and machine level computation. So they take the unstructured mess of the internet and turn it into something a computer can query or that can be reason over or talk back to us about something like having kind of a conversation, right? So one well-trained models becomes a universal language interface. So especially applications like ChatGPT have proved us that, right? So that's why almost every new software roadmap has some feature like powered by LLM or kind of attack as powered by LLM. So that's why we think LLMs are big deals in those coming years. So this meme captures how an LLM actually works under the hood. It simply showcases how the LLM works. So at inference time, the model is basically a kind of a Wallace or grommet laying track. It looks at the context window, predicts the next token, appends it, and then repeats. So often thousands of times per second. So that's how the LLM works. It's simply doing kind of a next word prediction, or technically it should be next token prediction, right? So even advanced reasoning models like DeepSeek 67 billion or maybe Claude Sonnet do nothing more exotic than next token prediction. So the magic comes from the billions of learned parameters that give those predictions enough statistical sense to look like planning, memory, or creativity. But remember the downside: if the right continuation isn't in the model's training priors, it will still lay the track, sometimes into mid-air, right? So that's where hallucinations come from. So it always try to give us kind of an answer with this next token prediction mechanism, even though it can be wrong, right? So what is a large language model? So let's see what is an LLM. Formally, an LLM is a kind of a deep transformer network. It's kind of a neural network with billions of parameters. Uh, GPT-4 is rumored to be in 20 billion range, and Claude Sonnet is around 34 billion range, and some open source models like Deep Seek basis in 67 billion range. Likewise, it's lies in it formed with billions of parameters inside them, right? Those parameters are trained on massive text data. It can be ebooks, Wikipedia, or GitHub code, or academic papers, literally the whole internet, right? And those sources altogether trillions of tokens. So the training objective is brutally simple. Given the earlier tokens, predict the next one. So we minimize cross entropy loss, run that for weeks on clusters of H100 like GPUs, and when the loss stabilizes, we get a model that can autocomplete pretty much any text pattern it has ever seen. So an LLM isn't kind of a knowledge base or a rule engine. It's a kind of a giant statistical model of human language to turn or the tune so well that next token prediction suddenly looks like conversation, translation, or reasoning likewise. So that's kind of a basic or the simple idea of what is a large language model. So let's see how those LLM process text, right? So it's basically there can be three concepts. I'll go through all those three concepts in detail. And it can be formed as kind of a transformer architecture with those three concepts. So let's see what are those three concepts. So everything a large language model does, it can be writing code, drafting a poem, even passing bar exam questions, start with those three low level moves, right? The first one is tokenization. It breaks the sentence into bite-sized symbols called tokens. Uh, Simply, it splits the text into units or the tokens, right? And then the second one is embeddings. So in this process, it turns each token into a vector of numbers that the model can do math on, because all those neural networks are processed with uh, some sort of numbers, right? We can't input a kind of a text or a string to a model. So what happens inside is it uses some vectors or matrices and do some mathematical operations and do some prediction. That's what happens inside a neural network or the transformer architecture. So we have to convert all those text data into a kind of a number or a vector space, right? So embedding is the process that we uh, do this. And the next most important thing is the attention mechanism. So this was introduced by a paper called Attention is All You Need, which was published during 2017. So this is the process of like letting every token look at the others to decide which ones actually matter for the next prediction. So simply, it can be introduced as model focuses on relevant words for each prediction. Hope you got an overall overview or kind of a basic idea about those three concepts. I'll deep dive into uh, those three concepts next. So let's see what is tokenization and embedding. So when a prompt first enters a language model, the text is broken into tokens. Think of them as kind of a Lego bricks the network already knows how to handle. So common words such as the, cat, or amazing remain whole, but unfamiliar or very long words are snapped into smaller fragments. A medical term like which is shown in the slide, electroencephalography, might become five parts as elect, pro, hens, fal, and ography. So keeping a fixed vocabulary of roughly 50 to 100,000 tokens lets the model covers everyday English and rare jargon without storing a separate entry for every possible word in the universe, right? So this is what basically happens inside tokenization process. So after the tokenization, each token ID is passed through an embedding table. Embedding table means a kind of a huge lookup matrix that might be 100,000 rows by 4,096 columns in a system the size of DeepSeek 67 billion model. So the ID selects one row, returning a long vector of real numbers, and you can picture this entire vocabulary plotted in a multi-dimensional meaning space. So vectors for the doctor and nurse sit close together, while little vector arithmetic. Uh, this is something kind of a famous example like king minus man plus woman. leads you near queen, right? So it's kind of a space that those tokens can be placed based on the meaning or the semantic meaning, right? So these coordinates or the place uh, that are not hand designed, so they emerge automatically during the training as the model minimizes prediction error across trillions of sentences. So because the order matters, the network also adds a potential encoding to each vector, right? So that extra signal tells the model that, for an example, let's say dog bites man is not the same event as man bites dog, right? Even though tokens are same, but the meanings are not same with the placement. So uh, this placement is identically given as a kind of a unique number mapped to a vector that is called positional encoding. So combining those word embedding with its position code, and you end up with a rich numeric representation that encodes both what the token is and where it appears. So you can see it in the slide as well. From this point onward, the transformer never sees raw text again, because now we have turned those text into a kind of a number. So it manipulates only these high dimensional vectors. So if you like the visuals, imagine a kind of a panel that shows a sentence flowing left to right, then dropping into a colorful cloud of point label king, queen, doctor, and so on. So each annotated with its position in the line. So that mental picture sets the stage for the next slide, where we'll watch those vectors interact through the self-attention mechanism. So let's jump into attention mechanism, which can be known as kind of a intuition of the model. So inside every transformer layer, the model runs a quick group discussion among all the tokens it has just embedded, right? So this operation is called as kind of a self-attention mechanism, and each token creates three little vectors called name query, key, and the value, right? So you can imagine the query as a question the token is asking, which other words in the sentence are relevant to me right now. So it's basically, that means the query means asking or the questioning the token, which other words in this sentence are relevant to me right now. So the keys are short summaries or the uh, summaries that every other token broadcasts about itself, right? So by taking a dot product between one token's query and every other token's query key, the model assigns scores that say how strongly those words should influence each other. I'll repeat it again to give you kind of a clear idea. By taking the dot product between one token's query and every other token's key, the model assigns scores that say how strongly those words should influence each other, right? So take the sentence for an example: the animal didn't cross the road because it was tired, right? So when the model processes the token, the word called it, right? The highest query key score points back to animal, not to road, right? So for an example, if we do not have the query key score, so it can be referred as animal or road. But the query key is or the query key score is the factor that teaches us, or the teacher's model, uh, what it refers to, right? So hope you got that. And that high score becomes a weight close to 1, while the weight on road falls near 0. So the model then blends the value vectors using those weights. So it ends up carrying fresh information about animal and almost nothing about road. So in practice, the network repeats this trick in parallel across many heads. One head might track pronouns, another might watch for subject verb agreement, and a third could focus on punctuations, numbers of punctuations, right? So the beauty of self-attention is that it lets the model jump instantly to whatever the part of the sentence it needs, no matter how far away the word order, right? So earlier, we had recurrent neural networks. You might have heard about that. So recurrent networks had to march step by step from left to right. So the attention lets every word look at every other word in one matrix multiplication, which GPUs can do very quickly, right? So that's the amazing thing or the beauty in those in this attention mechanism. So after the attention pass finishes, each token's vector now contains a distilled view of the entire sentence from its own perspective, and that enriched information flows into the uh, next transformer layer. In short, self-attention is the mechanism that lets the model decide in real time what matters the most for the prediction of which it is about to make. Right? So hope you got an idea about attention mechanism. So let's see what is the transformer architecture is, and I quickly go through this architecture. So everything we have talked about so far, tokens, embeddings, or the self-attention mechanism, lives inside a repeating module called a transformer layer, right? So you can see the architecture picture as well in the slide. So it is kind of a two-step assembly line. So first comes the multi-head attention stage. Here, each token holds that uh, group discussion we just described, gathering the context it needs from every other token. So the moment that conversation ends, the token flows into a small feed-forward network, a miniature neural network that refines the information it just received, right? To keep signals from fading or exploding as they pass through dozens of these layers, the model adds two engineering tricks, right? One is a residual connection that lets the input of a block skip straight to its output and then mixes with the new computation, right? The other thing is layer normalization, that it rescales the number of or the numbers so that nothing blows up or shrinks at 0. So these shortcuts mean we can stack 50, 70, or even 100 transformer layers, and the gradient during training still reaches the earliest layers without trouble. So when you link many of those layers end to end, you get the full backbone used in models like GPT-3, Claude Sonnet, or DeepSeek, or whatever the model, right? So early layers polish surface layer level features such as spelling and syntax, and then the middle layers learn about concrete facts and simple relationships, and the deep layers combine everything into abstract ideas, the kind you need for reasoning or writing code. So throughout this entire stack, all computation is parallel, which is why modern GPUs or the TPUs can train a model on trillions of words in a matter of week instead of months. Right? So uh, if you want to imagine that, imagine kind of a two columns of Lego blocks, one labeled attention and the other labeled feed forward, repeated over and over with thin skip lines bypassing each block. So that is the highway an LLM travels every time it answers a question. So I hope you got a kind of an idea about how this tokenization or the embeddings or uh, the self-attention mechanism and the transformer architecture is. So now let's talk about how those LLMs think or how the next token prediction happens. So inside the model, thinking is nothing more exotic than supercharged autocomplete, right? So after the transformer stack finishes its computations, each position is in the sentence holds a uh, high dimensional vector. So the final linear layer converts that vector into raw scores for every word in the vocabulary, and a softmax turns the scores into probabilities that add up to 1. So imagine asking the model the capital of Sri Lanka is, right? The softmax might give Colombo or the Jayawardhanapura an 85% chance, and Kandy maybe 5%, and every other city a silver of probability. The system selects one token, adds it to the end of the text, and then runs the entire transformer again with the new token included. So, in other words, it always predicts just the next word, appends it, and repeat the loop hundreds or it can be thousands of times per second. So, this simple next token game explains both the brilliance and the blind spots of large language model. So because the training data covers uh, everything, almost everything, like news articles, novels, code repositories, or social media threads, and the model has seen patterns for almost any prompt a user might type, right? So that vast statistical memory lets it draft an email, finish a poem, or maybe kind of debugging a snippet of Python code by chaining together one highly probable token after another. So, but the same mechanism also means the model never pauses to verify facts or plan in a human sense. It only follows the path of highest probability through its learned space. When the correct continuation is missing from its experience, the model still produces a fluent guess, which can look like confident reasoning, or when wrong, uh, classic hallucination happens. Simply, in short, the thinking of an LLM man is an endless cycle of predict, append, repeat. So powered by probabilities learned from trillions of words. So this is what happens inside it. All higher level abilities, translation, summarization, even flashes of logic emerge as side effects of running that loop at enormous scale. Right. So let's see what are emergent abilities, right? So as we scale a language model or kind of a large language model, from a few hundred billion parameters to tens of billions, something surprising happens, right? So new skills appear even though nobody coded them in. So a 6 billion parameter model can suddenly add two numbers that a smaller uh, cousin always got wrong, right? Uh, Push the size further, and the same model begins to translate between languages it was never fine tuned on, or it uh, learns uh, or it learns to follow multi-step instructions such as sort these events by date, then summarize them. So these are called emergent abilities because they surface only after the model processor certain capacity and data threshold. So think of water turning to ice, more cold, and the liquid reorganizes itself into a crystal lattice. So in much the same way, extra parameters and extra tokens let the neural network organize its internal representation into something that looks like arithmetic, logic, or translation. So the key idea is that no engineer wrote explicit rules for those skills. So they emerge from the statistics of the training data combined with the expressive power of the transformer. So let's see some techniques that we can use to increase those thinking or reasoning or cognitive abilities of large language models. So there can be various concepts or the various tricks that we can use or various techniques that we can use, right? One is prompting. So through the prompt, uh, we can get those cognitive abilities, and some other techniques like reinforcement learning with human feedback loops, and some can be agentic reasoning and also integrating with knowledge graphs. So those types of techniques can be used to increase this thinking or the reasoning or the cognitive abilities of a large language model. So I'll discuss one part, that is prompting. So uh, in prompting, there are few prompting techniques like chain of thought, few shot, and tree of thought likewise. So I'll go through a couple of examples. The first one can be chain of thought prompting. So one way to unlock these latent skills is to ask the model to show it's working, right? So this is called chain of thought prompting. Instead of saying what is, for an example, let's say what is 12 times 13, and expecting a kind of a direct answer, we can ask model to give the cue like let's solve this step by step, right? So we can tell to model go through the steps, right? So it will gives us the thinking process of deriving the answer. So that short phrase tells the network to print a short reasoning trail before giving the final number. So you might have seen it in the GPT like platforms, or it is on DeepSeek as well. So sometimes when you use a model like O3 or uh, O1 or 4.1 in GPT, so the chat before it gives us the final answer, it states the middle steps or the thought process of getting the final answer, right? So in practice, the model now writes, uh, let's jump back to our previous example. 12 times 10 is 120, and then it can be 12 times 3 is 36. Add them, and we get 156 likewise, right? So the extra text guides the internal attention patterns, so they stay focused on the intermediate facts rather than jumping straight to the guess, right? So experiments show a big boost on multi-step maths and logic benchmarks once we use this style of prompting. So the important point is that we did not retrain the model. We simply changed the instructions or the prompt so that it spends more tokens thinking out loud. Right. So let's see how the few shot and in context learning works. So this is also another powerful trick to include a handful of example in the prompt itself, right? Suppose we want the model to translate English into French. So we start the prompt with 2 or 3 minute demonstrations, such as let's say, I am happy. So it will be in French as JSU's content, right? So likewise, we can include 3, 4 examples and ask us to give uh, the answer for our question as in the examples. So we can add our new sentence and let the model continue the pattern, right? So even though the model's weights stay frozen, it can generalize from those few in-prompt example. This is called in-context learning, right? So it works because the transformer is very good at spotting local patterns and extending them. So few short prompts can define not just the output language, but also the tone. So the format or even a reasoning strategy, right? So by carefully choosing those examples, we steer the giant uh, probability engine in the direction we want without touching any code or running any fine-tuning job. So that's what happens with those prompting techniques. And there can be some limitations and misconceptions as well. So fluency is not the same as understanding, right? So some people argue that they cannot uh, do the reasoning or they don't have any cognitive abilities. What they doing is like they do kind of a pattern matching, right? So the model does not know that Paris is the capital of France, or the Jayawardhanapura is not the capital of Sri Lanka. So it has only learned that the word uh, Colombo or the Jayawardhanapura almost always follows that phrase in the training data. So it might have seen that sentence in the training data. So when the training data are wrong or missing, the model can hallucinate an answer that sounds unbelievable, uh, but is false, right? So the context window is also finite. So a long conversation can push earlier facts out of memory. So bias in the data means bias in the output. So that means bias also can make a huge impact on the reasoning. And those small changes in wording can flip the answer completely. So most importantly, these models are not conscious, right? So they assemble sentences by pattern matching, not by reasoning about the external world the way a human expert would do. So this argument is going for a while, and you might have heard about this latest paper called "The Illusion of Thinking," or the understanding the strength and limitation of reasoning models via the lens of problem complexity. So up to this point, I have described reasoning in large language models as a layered pipeline, tokens, attentions, chain of thought, few in context examples, and it can feel convincing. Yet, fresh research, this was came from the Apple, remind us the story is not finished, right? So several teams, most recently, have run controlled experiments that poke at the limits of these apparent logic. And their message is not LLMs are useless, but rather the kind of reasoning we think we see is still fragile, right? So uh, on the Apple team has tried to like give a kind of a uh, three regimes. They shows us three regimes. On simple task, extra reasoning steps can actually hurt. On medium task, they help, and on very complex task, all current models collapse no matter how much step-by-step text they generate. Even though we give the algorithm to solve the final problem or the to get the final answer. So in other words, the model's polite explanations may only mask guesswork once a puzzle passes a certain difficulty, right? Uh, so the team built a set of logic puzzles with adjustable difficulty and tested ordinary LLMs against specialized reasoning versions that produce chain of thought traces. On easy questions, the reasoning models sometimes hurt themselves by overthinking and changing the right answer into a wrong one. So on medium questions, the extra reasoning help. But as soon as the puzzle complexity passed a certain point, both kinds of models collapse. So accuracy fell to nearly zero, and the verbose explanations became uh, empty words, right? So the takeaway is that today's chain of thought tricks create the appearance of reasoning, or the reasoning language models create the appearance of reasoning, but do not give the model genuine reasoning capabilities or the cognitive capabilities. So there's a ceiling we cannot break just by scaling parameters or adding more verbal rationality. So we have to find new ways how we can improve those cognitive capabilities of a large language model. So let's see where do we go next, or how we can improve those reasoning or the cognitive capabilities. So one research thread is reinforcement learning from human feedback, right? So this often shortened to RLHF. So after the base model is trained, we let humans rank its answers and then fine tune the network so that good reasoning uh, paths earn a higher score. So this technique has been used from the deep seek as well. A second thread would be as kind of an external knowledge graph or a kind of a more structured knowledge source to a large language model. So the model can fetch verified facts instead of recalling them from memory. So it's also a good approach, right? A third approach can be training specialized reasoning models like DeepSeek Math or Google's Gemini Prologic that focus their entire capacity on structured tasks. And also, we can have some agentic frameworks. This is also mostly used uh, a technique to increase those capabilities or the reasoning capabilities, such as AutoGPT, React, or also I have done some work on this area. My research paper is also published as Kara system. So these break a complex problem into parts hand them into a smaller expert tools or smaller set of agents, check the intermediate results, and only then let the language model compose the final answer. So each of these techniques chips away at the current limits. The most promising solutions will probably mix them all. Uh, a well-aligned language core, grounded in trusted data, surrounded by tool using agent that can plan, calculate, and verify. So that hybrid recipe is how we move from clever, or how we move from those language models to a where it can showcase some cognitive capabilities and do some complex reasoning up to the mark that we expect. So, and yeah, I hope you got a kind of a clear idea about uh, how those large language models work and how they learn to think and do the reasoning. And also, there are some argy going on that they aren't doing those reasoning capabilities for real. So they do kind of an illusion, like they only do the pattern matching or the pattern recognition and do the next word prediction. They aren't capable of doing much complex reasoning. But we should like find our ways to ha, uh, improve those reasoning capabilities of large language models through various techniques. So I have mentioned few. Hope you got a basic understanding of this area. And if you have any questions, I would love to answer them. You can scan this QR and connect with me on LinkedIn or whatever the social media network, and you can reach out to me. So thank you very much for joining, and yeah, thanks.
Thank you so much, sir, for that eye-opening session on how LLMs learn to reason. We have helped us understand a complex topic in a clear and inspiring way, and we are truly grateful for that. Before we conclude, we would like to offer a small token of appreciation to Mr. Nirodya Pussadeniya on behalf of the Microsoft Student Club of Wellassa University. Thank you again for taking the time to be with us and for sharing your knowledge and experience. Now, I would like to invite Innovate X Chair Chamodi Ahaso to deliver the vote of thanks. Chamodi, over to you.
Thank you, Rehini. Good evening, everyone. As we come to the end of this Innovative session, it's my honor to deliver the vote of thanks on behalf of the Microsoft Student Club of Wellassa University. First of all, a heartfelt thank you to our guest speaker, Mr. Nirodya Pussadeniya, co-founder of Synacal, for sharing his valuable time and insights with us today. Sir, your session opened our minds to the fascinating inner working of large language models, and you help us to understand how these advanced AI systems develop reasoning skills, and you made it both accessible and thought provoking. Thank you for showing us the depth behind today's most powerful AI tools and inspiring us to dive deeper into this field. We are truly grateful for your passion, your innovative work, and the way you motivated us to think critically and creatively in tech. A big thank you also goes to our amazing organizing committee and everyone who worked behind the scenes. Your dedication and teamwork but make Innovate a success. To everyone who will watch this session via YouTube, thank you for being part of our journey. We hope to see. Uh, we hope these sessions spark curiosity and encourages you to explore more in the world of AI and reasoning. We have more exciting tech lineup in our future sessions. So subscribe to MS Club UW YouTube channel to stay connected and updated in our upcoming sessions. Thank you once again for being part of Innovate X. We hope to see you in the next session. Thank you.
During the session, I have shared my screen. You saw the slides deck.
Yes, sir. We did see the slides.
Okay. Okay, then I hope everything's fine, and thank you very much for inviting me. Anything else?
Now we're going to wind up the session. Thank you, sir. And also, sorry if there was any
Okay, thank you.
inconvenience
See you.
happened. Okay, sir. Thank you.
Thank you, Jamode. And with that, we officially conclude today's Innovate X session. A big thank you again to Mr. Nirodya Pussadeniya, to our organizing team, to all of you who joined us. Let's stay curious, stay learning. See you again soon at our next event. Have a great evening, everyone.